Quizzes are graded in, by and large, we consider it one of two takes on it. Some of you, very myopic, small vision on it. You have to recognize that what we're going through and doing is obviously going to be very, very challenging. The quiz that you all got involved an AP pre-response question. You should be scoring, if you're looking to pass that exam, somewhere at a 60 or above. That's what successful looks like. You need to be getting 60% of those points. Those are all previously released but AP questions. Looking at some of you, though, you made some really, really, to put it mildly, well, I guess I'm not sure, dumb mistakes. There were dumb mistakes littered all over that paper. And you knew one thing, but you were answering the wrong thing. So we'll look at what we're doing today, though. This thing that you had in front of you was, what year was it? 2013, number 3. This question that you're going to go through and face, if you're serious about going through and taking the AP, and if you're seriously thinking about going through and signing up, these are 4 points that at a minimum, you need to be pulling a 3 out of 4 on. We'll show you the exact breakdown when we go through and do it. But if you are expecting success, you need to give at least 3 out of 4 points. So, taking a look at what's there, notice that this is a calculator-free question. The hot water is dripping through a coffee maker, filling a large cup. The amount of coffee in the cup at time t is given by that from 0 to 6 minutes. It's a differentiable function where it's measured in minutes. Now, we don't know what the function is, but we know it's a differentiable function. By the way, if we know it's differentiable, what then do we also know? Hands up, please, if you can tell me. It's continuous. That's going to play into our answer for B. Use the data in the table to approximate the derivative at 3.5 seconds. Hands up, please, if you can tell me what you would need to do to approximate the rate of change or the derivative at 3.5 seconds. Jake? I'm sorry, you said, I couldn't hear the second part. So you said take the values at what? Yeah, he's absolutely perfect. What'd you get? Okay, so your answer to the first question should look like this. Here's the whole thing. The derivative is equal to exactly what Jake told us. Flawless. Then he goes through and figures this out, and it ends up being 1.6. Nothing to do with the lives. Now, it should come out to be 1.6. Make sure that you get your units down as well. Who is this? What is this thing? We'll figure it out. Okay. Go take a look. We'll see a little bit. All right, looking at that, understand your approximation gets you one of the points and the units is the other. You have to make sure that you give out a full and complete answer. So mark on, and there's no, well, I was closer, you know what I meant. If these things are not there, you don't get any of the points. Now, the second question is very interesting. Is there a time between 2 and 4 at which the derivative is equal to 2? Justify your answer. So you tell me what you would need to do in order to answer out the B part of this question. We got one person, 2. Go ahead. Congratulations. You sound like a valley girl. Talking like that. Like that, whatever. Are you going to write? It's like that-ish, whatever. Yeah, give us a big consent. This isn't, J.B. Mackey. Now, his definition fell apart at the end. I'm going to tell you. The part that's so irritating is you're smart enough to give the answer. You're smart enough to, but you're not giving it. It's in between those ears someplace, but you're not giving me enough. But he was very, very close. And when you give the explanations, I don't want to ruin it for you. It's not cute to not be like, well, it's like this. It's not like anything. It is or it is. And you all are smart enough. I'll tell you this, you put in a hell of a lot of time in this course. Don't let your language be what holds you back. He gave the most important part, which was the justification. And he put something in there that I saw was missing at least on one paper earlier. You need to go through and apply the mean value theorem. Before you can apply the mean value theorem, what do you need to state? Thank you. What that means is, now here's a breakdown of everything that he said. Let's see how many points he gave. Did you say it's differentiable and continuous? Yes. According to yours, if I remember right, yes. The second thing is, did you go through and show that this equals 2? From what I understand, you did. From what you read, you did. Therefore, so now, this gets you 1 point. Finding that it equals 2 gives you 1 point. The second point is actually no math. You're stating, is it continuous and differentiable? And the answer is yes. We know that it's given. Given that the function is continuous and differentiable, we can apply the mean value theorem, which states that at least at one time over the open interval, it's got to take on that slope. Some way of saying that. But you have to be tighter on your language, because I hate for you to show all of that and put a like or whatever in the middle of that. Okay? Maybe you could draw that emoji where it's a girl like going like this. Whatever. Yes? Yes. It's continuous on the closed, differentiable on the open. Questions on that? Now, let's bounce over to our notes. But before, I'm sorry. Make sure you sign into your calculator if you haven't already. But I want us to this is a watch and see for just a minute. When we go over and deal with our stuff for today, what I need us to understand is this. I just said it's a watch and see for right now. Take a look. What I need you all to see is this. If this is my polynomial, you may be asked to evaluate out this polynomial at some really awkward value without a calculator. What needs to happen then is this. Let's say I asked you to evaluate out this polynomial at, evaluate out the polynomial at 2. Okay? So here's my where's my thing? Now, you're going to try to evaluate out that polynomial 2. And the equation is going to probably look maybe something like this. It's got to be to an odd power, 1/5, maybe x to the 5th plus 2/97 x to the 4th minus 11/3 x to the 3rd, and so on. See how that's awkward, and you're not going to be able to do that by hand. However, you can approximate what the function's value at 2 would end up being. And the way to do it is kind of easy. You can go through and determine what the equation of the tangent line is at 2. How could you figure out what the equation of the tangent line is at 2? What information would we need? So far we've got 0 persons. That's fabulous. What? We need the derivative, and then we're going to evaluate out to figure out what the slope is What else do we need to know in order to give out what the equation of the tangent line is going to be? What? What point are we going to use to evaluate it out at 2?
Or like, what point is that?
Well, it'd be 2 and whatever that y value ends up being. But he's right, you use the point at 2. So far, we go through and use the derivative at 2. That gets you the slope. And then the second thing is, we've got an x and a y we need, but we know the x is 2 and the y is something. So we could go through and figure out what that is. Now, what you're going to have to understand is, that works to approximate the function value at 2. But what if I ask you to evaluate out this function at like 2.01 without a calculator? Sorry, that's the derivative of 2.01. If I asked you to evaluate out the function at 2.01, you're not going to be able to plug 2.01 in and do all those operations. But what you can do is say, well, even though I don't know what the function's doing at about 2.01, which is just past 2, you do know what the tangent line is doing at 2.01. This right here, so 2.1 would be right close to it. Which one do you think it would be easier to evaluate out? The function, that swinging gigantic polynomial, to evaluate that out at 2, or to evaluate out the line, sorry, the poly at 2.01, or would I evaluate out the line at 2.01? Which one do you think would be easier? The line. Is the line exactly the same as the function value at 2.01? Is it? At least you say no? No. Is the line close at 2.01? Is it close at 3? No. So, we'd have to, if we were to evaluate it out at 3.01, we'd have to get a new tangent line. But see how if I pick a point really, really close, the line and the function aren't going to be that far apart. Does that make sense? Yes or no? Okay. Our stuff today is all predicated on that. It's called a local linearization model. Now, what you need to do, though, before you go, local linearization tells us we can use a tangent line to approximate a function as long as we pick a sufficiently close value to get the equation of the tangent. So I might not know what the tangent line is doing, but I can zoom in and give something really, really close. Now, what we're going to do, let's bounce forward, please. Take a look. You should be at or around page 10 in your notes. What page are you all on? 12? Fabulous. Go through, please, and let's look at line 12. Now, our steps for this are going to be profoundly simple and very, very redundant. In order to figure out our local linearization, because you're taking a the reason it's called a linearization, you're taking a nonlinear function and using a line to approximate it. And in our case, we're always going to be able to get a really good line because we know how to take the derivative and we can get a line of tangency that's nearby at every time. So this process has about 4 steps every time. See how this right here is our function? This right here is our tangent line. I don't need to know what the function is doing. If I can get the tangent line, I can use that tangent line to approximate the function value. Now, the further that I go away from the common point that they share, or the point of tangency, the further I go away, the worse that approximation gets. But for our purposes today, what you've got to go through and do is, our first step, step 1, is to determine the slope using the derivative. That's step 1. Probably going to want to write it down. The second step, determine the equation of the line of tangency at that specific value. The third thing that you're going to go through and do is evaluate out the line of tangency at the desired closer value. And then the last thing that we're going to do is to use that line to approximate out what the function's value is going to be. So there's a whole mess of stuff going on. Now, with that in mind, let's answer out our first question. Find the linearization of that at 1, meaning what's the line of tangency to it at 1. And then we're going to use that line of tangency to approximate the function value at 1.02 without a calculator. Then we'll check to see how far off we are with the calculator. But I'm going to guess it's pretty darn close. First thing up, I need to figure out, Hannah 1 is what? Okay, so what's my derivative going to equal? Can you give me what the slope would be? We're on fire. Davey, what would you do next? Okay, so what do we need in order to figure out the line of tangency? What? A point? Which point do you want to use? Nope. That's what we're going to try to approximate using this line. 1. So let's evaluate out my function at 1. And we get out of 1. So, what's the equation of the line of tangency going to end up being, Jake? Plug your slope in. Our slope is 2. So what would this be? Solve it out for y. Now, we're going to use that line to approximate what the function does at 1.02. So, how could I figure out about what value the function would take at 1.02? Well, let's evaluate out what our tangent line tells us. What does the tangent line tell us the value of this function would be at 1.02? I go through and take this. Now, don't use a calculator. I know it's big kid math. Evan, are you ready? Did you get adequate sleep last night?
Not really.
Okay. Wow. How many hours? That's it? Wow. 8 hours for your brain to go through and reset. Now, if you can't, if you need to tap out, it's fine. What's 2 times 1.02? Now, an easy way to think of it is, imagine you're working at McDonald's on the register, and the person says, I'll have this item, and the item comes out to be $1.02. And they say, wait a minute, young man, I'd like a second item before. How much money would they have to give you?
2.04.
Now, let's say they also have, I've got this Super Savers coupon where I take one of the dollars away. So how much now do they owe you?
1.04.
Boy, that's terrific. So now, we could go through and reasonably conclude that what does the function approximately equal? Hands up, please, if you can tell me. What does this function approximately equal at 1.02? Hands up, please, if you can tell me. What does this function approximately equal at 1.02? Seriously? Jason? No, we can go more than just 1. 1.04. Because that's what the tangent line equals. And the tangent line is right next door to my function. Now, go into your calculators, please, and evaluate this function out at 1.02. So you can do x squared bar x equals 1.02, etc. What? I can't even hear you. You're mumbling.
Move right on.
Yeah, we're adjacent to the right answer. What did you get? Wow. Not bad. So are we close with our line? Is it nearby? You bet. Take a look now at the next question. Find the linearization of this at 1. Find the linearization of this at 0. Use it to approximate those two values and check the accuracy What happens to the accuracy as x moves further from the point of tangency? You can answer the second question before we do the question out. What happens to the accuracy as x moves further away from the common point that the line of tangency in the graph share? You tell me. What happens?
It's less accurate.
What? Not bad. That's perfect. I think you even stole what I did before. Did you watch last year's video before class? Okay. I actually had students before that did that. A plus. Did you know that?
Probably 8.
Let's start off. What would my first step be to do this out, Sam? Okay. And then what would you do once you put it as x? So take your derivative, and what would it be? Are you tired, Sam? Did you get less than 5 hours? Or less than 6? Okay. That's 6 hours, that's it?
Need about 9.
Go ahead. You've got to remember, loves, that you've got to apply the chain rule here. Outside, inside rule. What's the problem? Our derivative is going to be 1. Got things to do, honey. Now, taking a look at what's there, I rationalized it. I made it look beautiful. Now, this is what happens. I need to evaluate this out, find the linearization of its 0 used to approximate those values. So the first thing up is I found my derivative. The next thing that I go through and do is let's evaluate out our derivative at 0. So this should be a big extension for us. Liam, what's the value of the derivative at 0? Not B. Pick the lower one.
Oh, wait, no, I did it right. I just want to have.
Okay. Don't yell at me. What do we do now? Abby? What's that? Not yet. We're trying to build up the tangent line. What do we currently have in order to build the tangent line?
Oh,
So perfect. We need to figure out that y value. Hands up, please, when you can tell me what f of 0 is so I can figure out the y value.
1.
Okay? So now I go through and evaluate out f of 0 and get 1. Go through right now, determine what the equation of the line of tangency is given in y equals 4. So go through and do that out right now.
Somehow getting Jack.
Jack? What'd you get?
Y is equal to 1/2 x plus 1.
Not bad. Now, Megan, what would we do next? We're going to need to evaluate that out at 2 different values. Careful. We're not going to use the original function. We're going to try to evaluate out, get something really close to that original function. We're going to evaluate out the tangent line at 0.05. So, what I'd like us to do is, we'll start off and let's evaluate out the tangent line at 0.05. Now, this is going to be tough for some of us. So you've got, like, think of it this way. That's the same. Think of the money, right? How much money is that? A nickel, which is 5 cents, right? So now I need to take 1/2 times 5 cents and then add $1 to it. How much is 1/2 of 5 cents going to be? Hands up, please. If you can tell me. or what's 1/2 of this value going to be? Either way, it'll help you out if you ever have to go through and make change in your career. Not change your career, but make money change. The boss will probably force you to change your career. Molly? And then, what do you need to do to that amount? Now, it's a lot, so slow down. What's 0.025 plus 1 minute? Not too shabby. That approximates. Is it equal to the function? No. It would be like this. Let's say I want to know what kind of neighbor John is, right? Now, I'm not going to ask John. Instead, I go to you. You sit right next to him. Is he a good neighbor or not? Is she going to give me a 100% accurate description of John? Is she going to give me a very, very accurate one? Yes. Flaws and all. Penmanship is poor. He writes too small, too quickly, a little too cash on his definitions at times. Like he's got other things to do when there's nothing better in life than doing calculus. Jack, oh look it, you're up again. Jack, what happens now? What else do we have to do? Now, Jack, I want you to brace yourself because it's going to be a very difficult thing. Now, think of it like this. 0.2, how much money would that be? 20 cents. All right. Now, we're going to walk you through this nice and slow. Did you get 6 hours last night? Okay, good. 7? You don't know? What time did you go to bed? And what time did you wake up? So that's how many hours? 7. Good. Math is all around you. You use it every day. Now, Jack, ready? If you have 20 cents and someone takes half of it, how much do you have now? 10 cents. And then someone comes along and gives you a whole extra $1. How much is that? Now, that is terrific. And that's our approximation to the function at 0.2. Now, what you're going to do is this. Go into your calculators, evaluate out the function at 0.05, and evaluate out the function at 0.2. Let's pull someone's calculator. I bet you we got lazy Larrys who haven't even signed in yet. Oh, just 1, 2.
Just Jason.
Jason and Evan. Maybe they're too far away. Maybe I'll bring them right up front. You can sit right at my desk. Whomever this is terrific. Look at this. Fabulous. Who is this? Who's going to take credit for it? No way it can. No way. Molly. Boy, you are a pro. Now, let's ask this, Molly. What did we say, according to the line, what is the function's value at 0.05? Now, is 1.025 close to this value?
Somewhat close.
Somewhat close, right? It's only a 1,000th off. A little bit more than somewhat. What about the one Jack did for us? What did we get there? Was it 1.1?
Yeah.
Is this close? You bet. So is it 100% accurate? No. Is it really, really close? Sure. But now let's ask ourselves this. Who's the genius we had before? Was it Molly? Was it you? I think I laud the fabulous answer previously. Molly? What did you say, the last part of this? What happens to the accuracy of x as it moves further away from that common point that the graph and the line of tangency share?
It gets less accurate.
What gets less accurate? Stop saying it. It's like cursing at me. Yep. The line gets, the further you move, further x moves from there, the less accurate the estimate becomes. The less accurate my line of tangency becomes. See? Perfect. Boy, he never gives up. You wouldn't think of it by looking at it. But there, I bet, is at least 4 or 5 thoughts that happen between those ears every day. And he goes through and says, I don't know as much about John. Because he's so far away. Are you friends on the Twitter? Okay. Do you instant face chat each other? See? I knew it. I knew it. It's a new app I'm coming out with. There was one on The Office, I think it called it like Woomph or something. The guy Ryan was going to make, where it was just every app did all at the same time. So like, if you did something, it was like, it started barking. It was like if anyone on any social media did anything ever. By the way, when I don't know, I think it was in college when it happened. There was an app called Friendster, which I still think is the best name for an app ever. And maybe if you invent something, you could call it Friendster.
Well, since it's already created, would we not be able to do that?
You could spell it with a Y or something like that. Friendster. By the way, is there any juniors in here? So we don't have to do course recommendations. You know what my recommendation for you is? Study. No. You all are bright people, don't get me wrong. What? Everest Institute. I think poor Thomas, I remember Thomas, now he's not here today. Thomas came in and he was all sad. Because Everest was closed. I can't remember, I thought that it was him. Or maybe it was me that drove by. I can't remember, but I just remember looking and it was like on the tennis bus one day we were leaving like a Wendy's in Monaco. And we saw it like closed for business. You know, just in general, on a side note, if your college's main source of recruitment is advertising during Judge Judy, it's probably not quite up there with Yale and Princeton. I don't want to, DeVry. Always, and that's at ITT Tech. Listen, I'm sure they do some fabulous things. If you can't go to it, point to where it is on the map. It doesn't exist. A general thing. Where is the
Roberts
ITT?
Wesleyan? Like,
What? What's Roberts Wesleyan?
Exactly.
No, I don't know. Is it? Is it a local one?
Yeah, it was
Okay. Is it a rock? Is it
Yeah.
Okay. Where's the one? The one? No, there's. Well, the one that I see now on Judge Judy all the time is ITT. And if they advertise on the Cartoon Network, that's also not a good sign. If you ever tape or Adult Swim or something, is watching Family Guy. It's generally bad. Now, we're going to learn about Leibniz notation today. And Leibniz, this is one of the things that's fascinating. Newton, two people were essentially working on calculus at the same time. So you're going to see times where we're going, well, wait a minute. That crazy old lady told me that when I go through and do this, I write f prime. And then someone else will go through and say, well, then sometimes I'll use dy dx. That's a difference in authors of calculus. There's two people, Newton and Leibniz. So Leibniz notation is slightly different. Newton, in all honesty, I actually think, if I remember from History of Math correctly, there's a math test you can take called History of Math, which is a fascinating test. We'll even say, I think I have a book about it, but there's people that fought wars, and it's very culturally dominant. I think Leibniz was French, and Newton was English, which is why in most of the English-speaking world we use Newton's notation. On the other end is Newton was a much more influential mathematician. In any case, Leibniz notation, though, is quite important to know because you can use it to easily show where things are going. Leibniz used the notation dy dx to represent the derivative of y with respect to x. We've talked about that before, especially with implicit differentiation. It looks like a quotient, but in reality, it's nothing more than a limit of quotients at which both the numerator and denominator are approaching 0. Now, somewhere in here I have it, but in any case, like there's this book which you can go through. Now, like you all laugh, you're like, oh my god, it's a book that's smart. Yeah, welcome. So you can go through those, like look at it goes into depth, right? This is something you know. Area of a triangle, if you got two sides, 1/2 AB sine C. Remember that? Yeah. It goes over the math as to why. It talks about like bearings and locations. These are similar questions to like the stuff that you do in Algebra 2. In any case, and it goes all the way up to parametric equations. There's stuff about integrals. I'm trying to think of what else. Yeah, introductions into calculus and stuff like that. It's really, really fascinating. But the reason I was going to show you, by the way, we're going to do this, which is volume over torus, which is a donut. In any case, there's people who have actually, and I thought I had it. There's a book that's a very fascinating read. It's called Zero, the Story of a Dangerous Idea. And it talks about how people have actually, mathematicians have been executed publicly for talking about division by zero. And you laugh, but it was contrary to church teachings at the time. Like they were trying to, the old Roman Catholic Church was trying to, and the Pope were trying to suppress mathematicians and scholars. And I don't want to ruin it, but you can't argue with math ever. And they, like, it was when they were struggling with the fact that the Earth wasn't at the center of the solar system, which was a radical idea that for a time, I think it was Galileo was excommunicated from the church for a long time, if I remember that correctly. But in any case, and things they made up at the end. But you had people who were saying division by zero. The notion of zero was a profound and almost illegal concept for a while, because the church was going through and saying it's impossible for nothingness to exist. And in math, you're going through and saying it's quite possible for nothing to exist. If I have 5 apples and I take 5 away, that's 0. And in theorems, if you can't grasp what 0 is, or it's not commonly accepted, people would go through and say things. And there were people who, believe it or not, were publicly executed because they published papers that centered around proving 0 existed. Which was fascinating. If I can find the book, it really is a really good read. It talks about why division by zero doesn't work. You think of it like a rubber band. Like if you multiply something out, you're stretching, and division is a compression. But what happens if you go through and divide by zero? It's essentially like letting the rubber band go, because there's nothingness there. So it's a very good way. It actually should be probably reading for all high school kids. But anyway. Let y equals f be a differentiable function. The differentiable dx is a dependent value. The differentiable dy is equal to, remember, because what we're saying is the derivative of y, dy, dx, is equal to f prime. Well, if I solve it out for dy, I multiply both sides by dx. You're using the chain rule on this. Keep in mind, dy, the derivative of y, is equal to the derivative of the function times the derivative of the argument, which is the input. And what's the derivative? Now, the reason that we put this down, the derivative of the x is what goes on the inside. Now, for our stuff today, given that function, find the differential, dy, which, by the way, what's the dy the same as saying? No? It's the change in y. dy is the change in y. And evaluate it out when x equals 2 and the change in x is equal to 0.1. Now, let's watch how this works. We'll walk it through, hopefully slowly, the first one, but hopefully it makes sense. It's just an alternate way of saying the same thing. So I'm going to start off with that function. Now, when I do this out, I go through and take my dy, which would be equal to the derivative of the function times the change in x. Well, we need to solve this out, except we can now start making some replacements in. What is the change in x going to be in this case? Hands up, please, if you can tell me. You've already defined it. What's the change in x, Leah? There you go. So we go through and say dy is equal to, and we know what our x is. We define the x as that. This is going to tell you what your derivative's value is at 2. A close approximation to it. This is why Leibniz notation, and Leibniz wasn't the same academic titan that Newton was. So now we go through and evaluate this out. 2 times 2 gives me what? 4 plus 3 gives you 7. and then times 0.1, so the change in y is equal to 0.7. So now what we're going to say is this. We can give ourselves an estimate of what the derivative is going to be. You would take the function value at 2, and in this case our function value at 2 would end up being 10, and then evaluate out what the change in y would be at 2. So what did we get our change in y to be? 0.7. Sorry, 2 point, to go 1 unit away. Let me say this again, we'll slow it down. If you know the function value at 2 is equal to 10, now let's approximate what the function value at 2.1 is going to be. Well, it's equal to what the original function value is plus the change that you get from going away from that function value, 0.1 units. So you know the function at 2 is equal to that. The function at 2.1 would be that same value you got at 2 with 1/10 more, or the change at 1/10 more on there. So that's why this would come out to have a value of 10.7. Now, this is what we get using that approximation. So the change in the value from 2 is 0.1 away, and it will be approximately 0.7. So we're saying if I'm there, the change is that amount. That lets me find out what the function value is going to be. And if we plugged it into the calculator can evaluate out the function at 2.1, and it comes out to be 10.71. Are we close? Were we close? Without a calculator, we were close. Now, we've got 2 more that hopefully we can burn through fast. A radius of a circle increases from 10 to 10.3. Estimate the resulting change in area. Now, we know what the radius itself is, and we know what the change in the radius is. What's the change in the radius going to be? Hands up, please, if you can tell me. Yeah? 0.1, and what's the radius itself? 10. Now I'm going to look at the derivative formula, and I'm going to take its derivative. Keep in mind, for some of you, this is a struggle. Pi is not a variable, it is a constant. What do we get if we take the derivative of the left side? Hands up, please, if you can tell me. No? Look at the formula. Take the derivative of the left side. Yeah? Careful. The derivative of the left would be the derivative of the area is equal to, now it would be 2 times pi times r times the derivative of the r. Now we can find out what the change in area is about by going through and plugging in. What's the r value going to be, Sierra? And what's the change in r going to be? So I go through and make my plugs in. And what is that going to come out to be? I think that this is an approximation. Oh, sorry. 2 pi centimeters squared. That's what the change in the area is going to be by doing that. We've got one more, and it says the diameter of a tree is 10 inches. During the following year, the circumference increased by 2 inches. So right away, I know my circumference formula, 2 pi r. What did the circumference change by? 2. Was it a positive 2 or a negative 2? So the change in the circumference is equal to 2, if you need to see it. We also know the diameter. What's the formula for diameter? The diameter is 10 inches, and the formula for it, oh, and the radius is that, sorry. You could do 2 pi r or pi d. That's why I listed both of them, because I think that even you two were debating over which one to use. Doesn't matter as long as you stay consistent. How much did the tree's diameter increase? Well, I start off and say, there's my circumference. Circumference is equal to 2 pi r. From there, I go through and take the derivative of both sides. So the change in the circumference is equal to how much? Hands up, please, if you can tell me. Leah? What's that? Terrific. Times dr. But what's the dr value going to be? Well, we don't know, but what's the change in the circumference equal to? 2. So how can I solve for the dr, or the change in the radius? How can I solve for the change in the radius? Yeah, and what would we get? 1 over pi. That's equal to what the change in the radius is. Now, how much did the tree's diameter increase? Remember, we found the change in the radius. What do we do to find the change in the diameter? Double it. What is pi over 1 over pi plus 1 over pi? You did a terrific job today. You're all-stars. ASTC. All-star trick class. What? Do what you want. Don't say it that way.
Yep.
You're going to be...
You're terrible. It's freaking terrible. No, just make it rain. Go, Josh.
Yeah.
When that window closes, it is closed. How many? Good for you. Good for you. I'm proud of you.